Imagine a universe where planets wander aimlessly, stars burn unpredictably, and even atoms constantly transform. Chaotic, isn't it? Fortunately, our universe isn't like that. Instead, it's a grand symphony governed by exquisite and beautiful laws of physics. From the dance of galaxies to our very existence, everything adheres to a harmonious set of principles. Join us as we explore the magnificent harmony of the worlds, the physical laws that have shaped the universe we inhabit. Welcome to SpaceTime's journey of cosmic discovery, where we uncover the universe's deepest mysteries. In this video, we will explore the Milky Way and its undiscovered secrets. Don't forget to subscribe to the channel so you don't miss out on other exciting space exploration videos. If you find the video interesting and helpful, please like and share to support us.
For millennia, humans have gazed at the night sky, striving to find order in the intricate movements of stars and planets. From that curiosity emerged one of science's greatest milestones, the birth of classical mechanics and Isaac Newton's law of universal gravitation. Before Newton, Johannes Kepler dedicated his life to deciphering the mysteries of planetary motion. With extraordinary perseverance, Kepler discovered that planets do not move in perfect circular orbits, but in ellipses, with the Sun at one focus. He also elucidated the relationship between the orbital period and radius of planets, revealing a hidden order behind the celestial dance. Kepler's laws were crucial stepping stones, laying the groundwork for greater discoveries to come. After Kepler, Newton connected these disparate pieces into a cohesive picture. He realized that the force that causes an apple to fall to the ground is the same force that keeps the moon orbiting Earth and Earth orbiting the sun. That is the law of universal gravitation, a universal rule governing all massive objects in the universe. This law, along with Newton's three laws of motion, transformed the universe into a giant clockwork mechanism where every movement could be predicted with astonishing accuracy. From this, we can understand tides, the orbits of comets, and even the formation of galaxies.
However, Newton's perfect cosmic picture faced challenges as we began to explore its limits. At very high speeds or in extremely strong gravitational fields, Newton's equations were no longer accurate. It was Albert Einstein who bravely overturned the concept of absolute space and time, ushering in a new era of physics with the theory of relativity. Einstein's special theory of relativity, published in 1905, shook the foundations of classical physics by proposing two bold postulates. The laws of physics are the same for all observers moving at a constant velocity relative to each other, and the speed of light in a vacuum is the same for all observers regardless of the motion of the light source or the observer themselves. This led to astonishing consequences such as time dilation and length contraction, demonstrating that space and time are not independent entities, but two aspects of a unified entity, space-time. Later, in 1915, Einstein went on to publish the general theory of relativity, a true masterpiece of scientific thought. In this theory, he described gravity not as a pulling force between objects, but as the curvature of space-time caused by mass and energy. Imagine a stretched-out flat sheet. When a heavy ball is placed on it, the sheet sags. Smaller balls rolling nearby are pulled into the sag not by a direct pulling force, but by the curved shape of the sheet. Similarly, planets orbit the Sun not because the Sun pulls them, but because the Sun's immense mass has curved the surrounding spacetime, and the planets move along the shortest paths in that curved spacetime. This theory successfully explained phenomena that Newton could not,
such as the precession of Mercury's perihelion and the prediction of black holes, which Stephen Hawking detailed in his A Brief History of Time. It expanded our vision of what might exist at the farthest reaches of the universe. However, as we delve deeper into the subatomic world, the cosmic picture becomes even stranger and more unexpected. At the subatomic level, the laws of physics that Einstein described no longer hold true. Instead, we enter the realm of quantum mechanics, a field riddled with paradoxes and incredible possibilities.
Quantum mechanics reveals that elementary particles, like electrons, do not exist in a definite position or state until we observe them. They can exist as both waves or particles, wave-particle duality, and can be in multiple states simultaneously, a concept known as superposition. Heisenberg's uncertainty principle, a cornerstone of quantum mechanics, asserts that we cannot precisely know both the position and momentum of a particle at the same time. The more accurately we know one, the less accurately we know the other. This stands in complete opposition to the certainty and predictability of classical physics. Quantum entanglement is another phenomenon of the quantum world, where two particles can be mysteriously linked regardless of distance. Measuring the state of one particle instantly affects the state of the other, seemingly transmitting information faster than light, something Einstein called spooky action at a distance. These discoveries not only challenge intuition, but also raise profound questions about the nature of reality, the role of the observer, and the connection between the smallest constituents of the universe, hinting at complex concepts like the multiverse, mentioned in the book The Universe in a Nutshell. Despite the complexity and distinct differences between the macroscopic world of relativity and the microscopic world of quantum mechanics, the entire universe is still governed by a handful of fundamental forces. There are four main forces that govern all matter-energy interactions in the universe: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Their delicate balance is key to the existence of the universe and life as we know it. Gravity, as we know, keeps planets orbiting stars, stars clustering into galaxies, and galaxies forming clusters. It is the weakest force, but has the greatest influence on a cosmic scale. Electromagnetism governs interactions between charged particles, holding electrons around nuclei, forming atoms and molecules, and is the foundation of light, electricity, and chemistry. Without electromagnetism, there would be no chemical bonds, no life. The strong nuclear force, as its name suggests, is the strongest force, holding protons and neutrons together in the atomic nucleus. If this force were slightly weaker, nuclei would be unstable, and no elements heavier than hydrogen could form. If it were slightly stronger, stars would burn too quickly or fail to form the elements necessary for life. Finally, the weak nuclear force is responsible for certain types of radioactive decay and drives the nuclear fusion process in the Sun, providing energy for life on Earth. Each of these forces plays an indispensable role, and even the slightest adjustment could lead to a completely different or even non-existent universe. One of the most astonishing things about the laws of physics is their fine-tuning. The fundamental physical constants of the universe, such as the gravitational constant, the mass of the electron, or the speed of light, appear to be calibrated with extreme precision to allow for the emergence of life. For example, if the strong nuclear force were only a few percent stronger or weaker, carbon or oxygen, essential elements for life, could not form in stars. If dark energy, the universe's repulsive force, were slightly stronger, the universe would expand too rapidly, not allowing enough time for galaxies and stars to form. This seemingly incredible coincidence has led to many philosophical and scientific debates. Is this merely pure randomness in an infinitely vast universe, or is it evidence for a deeper cosmic principle, perhaps even the existence of a designer? Some scientists, like Stephen Hawking, propose the idea of a multiverse,
where countless universes exist with different physical constants, and we just happen to live in one with conditions suitable for life. Whatever the explanation, this fine-tuning is a powerful reminder of the universe's profound and intricate harmony, raising questions about our place in this cosmic symphony.
While the theory of relativity explains the universe on a large scale and quantum mechanics describes the world on a small scale, a major challenge of modern physics is to unify these two theories into a theory of everything. Stephen Hawking dedicated much of his life to pursuing this goal, as presented in his works. A theory of everything would be a single, elegant set of rules capable of describing all physical interactions in the universe, from the formation of black holes to the behavior of subatomic particles. Leading candidates for the theory of everything include string theory and M-theory, which propose that fundamental particles are not points, but tiny vibrating strands of energy in additional spatial dimensions. These theories are incredibly complex and currently remain in the realm of hypothesis, but they promise even deeper insights into the harmony of the worlds and the laws that govern them. The search for this theory is not just a scientific goal, but a deep human aspiration to understand the deepest nature of reality, to see an underlying beauty and simplicity beneath the complex appearance of the universe. It is a testament to the belief that the universe, however vast and mysterious, can still be understood and deciphered by human intellect. The harmony of physical laws has created a universe that is both comprehensible and life-sustaining. But can we go further, transcend the barriers of space and time to truly explore the universe's deepest mysteries? In the next video, we will journey through space and time, learning about the limits, possibilities, and bold ideas of traveling through dimensions, a fascinating and challenging topic.